Hey everyone, welcome back to Trigonometry. This is going to be lecture 10 of the course. And in this section we're going to start looking at some of the key trigonometric identities from trigonometry. And as I said in a previous section, there are countless trigonometric identities that we could look at. And we saw a handful of examples in the previous lecture when we talked about how to verify identities. So what we'll try to do in this course is focus on on identifying really important trigonometric identities. And when I say important, what do I mean? Well, I mean identities that allow us to solve problems or verify additional identities, or potentially just identities that are very kind of interesting, right? They have a certain kind of interesting quality to them. And so we're going to start with some of the most useful trigonometric identities, and those are the sum and difference formulas. So let's go ahead and jump into it. And we'll call this section 3.2 sum and difference formulas. Okay, and so I'm going to start by just telling you what one of the examples of the sum and difference formulas, and then we'll talk about how to derive it, where it comes from. So the cosine was the one we're going to look at. The cosine of the difference of two angles is the one we'll look at. Okay, and here's the formula, and I'll tell you the formula, and then we'll use a very clever derivation to explain how this is true. But the formula says that the cosine of an angle alpha minus another angle beta is equal to the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. Okay, and so this is one of the sum and difference formulas. And so basically, and I guess we would consider this a difference formula. So you've got the difference of two angles, alpha and beta. So alpha and beta are two angles. They could be the same angle, but they don't have to be. In general, they do not need to be. So if I want to calculate the cosine of the difference between an angle alpha and another angle beta, then I can calculate it directly like this, obviously, or I can use this formula in its place. Okay, and so where in the world does this come from? So I'm going to go ahead and we're going to do a derivation. We'll derive this formula, and it's a slightly complicated derivation. But it's nothing that we can't handle. Okay, so we're going to start by, what we really need is the upper portion of a unit circle for this derivation. Okay, and so I've got the upper portion of this unit circle, and somewhere on here, so this would be like the center of the unit circle, and somewhere on here I'm going to put a point, and I'm going to label the point P, and we know that that point P is cosine of some angle beta and sine of some angle beta, right? And so obviously the angle that that point P makes with this intercepting ray is beta. Okay, so I've got this beta right here. Okay, and somewhere over here I'm going to put another point on the unit circle and connect it to this ray, and it is going to be labeled as alpha, right? So this is the angle that starts here and goes all the way around. And I'm just going to call this point Q. Okay, and we know that Q is as an ordered pair could be thought of as cosine of alpha and sine of alpha. Okay, all right. Right, and so hopefully that's clear, right? You can think of this as having, this sort of horizontal component, which is the cosine of beta, and you can think of it as having this vertical component here, which is the sine of beta, and the same thing would work over here, right? You'd have the cosine of alpha and the sine of beta. Okay. All right. So let's just call this diagram 1. Okay. Now, between these two angles, there's a third angle that's implied here, and I'm just going to kind of draw it like this. And you can think of that angle as this whole angle alpha, right, minus this angle beta. So this is alpha minus beta. Okay, this angle between these two rays. Okay, that's alpha minus beta. Okay, and let's go ahead and connect this line here. And so this is going to be our diagram 1. Okay, this is going to be our first diagram. Now it's important to note that the equation of the circle here is x squared plus y squared equals 1. Okay, that's the equation of this circle. All right, in this case, the semicircle. Okay, so this is the first picture we need. Now I'm going to draw a second picture that's basically supposed to be the same semicircle. We'll see if I can draw it properly. It's not too bad. Okay, we're going to call this diagram 2. Okay, now I'm going to, what the idea with diagram 2 is that I have this triangle in diagram 1. Now what I want to do is I want to shrink, I want to hold all these angles internal to this triangle constant, but I want to shrink beta down, which basically means I want to take this line segment here and rotate it down until it comes into contact with the positive x-axis. Okay, so that means I want to bring P down to here, right? And so when I do that, what does P become? Right, again, assuming this is the origin, this is the positive x-axis, P is equal to 1, 0. Right, so I just rotated this down until it's on top of the point 1, 0. Okay, now Q, if I'm kind of preserving this triangle, Q is going to have to rotate up, right? And so Q is going to come up some ways, and we'll talk about what Q is in a second, but let's make sure we're oriented here. Right, so I've basically rotated the triangle until the side here is in contact with the x-axis. Okay, and so when that happens, beta basically becomes 0, doesn't it? Yep. And so what is the angle here? What is this angle here? Well, just kind of looking over at this triangle, we can see that that angle must be this alpha minus beta. Right? Does that make sense? Hopefully it does. Right? Alpha minus beta, that's what that is. Right? Okay. And so what is Q as an ordered pair? Right? Over here, Q was cosine of alpha, sine of alpha. What is Q over here? Well, over here it's cosine of alpha minus beta, sine of alpha minus beta. Right, that's what this angle happens to be. This internal angle hasn't changed, right? That was part of the deal when we rotated this P down. We were going to bring Q along and preserve this triangle. So that's what we have here, right? So inside here it's alpha minus beta. It's also alpha minus beta over here. Okay? Okay, and it's important to notice here that this circle is the same circle, so it still has the same, x squared plus y squared equals 1 formula, right, for that circle. Okay, all right, and so those are the two pictures that we need, and what we're going to do is we're going to set up some equivalencies between these two triangles. Okay, and so we're going to start with diagram 1. Actually, before I do that, I do want to talk. We have to talk through one other thing, and you may have seen this. This is called the distance formula. And so the distance formula, this is from algebra. If you have 2 points, so let me write it out here. So given 2 points, x1, y1, and x2, y2. the distance between them is, so it's like d, and then you basically take the difference of the x coordinates, square it, add to that the difference in the y coordinates, and then take the square root. Okay, so this is the distance formula. This is something you've probably seen in algebra, right? This is something you've probably seen in algebra. Now, what we want to do is we want to figure out the distance between P and Q. Right, it should be the same over here as it is over here, right? Because the triangle is the same. It's still inscribed in the exact same circle. Okay, so what is the distance between P and Q? So that's kind of the question that's going to drive this next section. Okay. And so we're going to look at diagram 1 for this. So from diagram 1, right, what's the distance between P and Q? Well, I know the coordinates for P, it's cos beta sine beta, and I know the coordinates for Q is cos alpha sine alpha, right? So PQ, I'm just going to write it like this, and we know that that means the distance. It's going to be equal to cos alpha. So basically you take the x coordinates and subtract them, right? So cos alpha minus cos beta, and then you square them. So cos alpha minus cos beta, and square it. That's this piece. And you also do the same thing for the y components, right? So sine alpha minus sine beta. And you square that. And you add those together, and you take the square root. That's just the distance formula applied to this line segment PQ. Okay. Now we're going to do some algebra here. All right. So here's where it gets a little bit messy. All right. But basically, we're just going to expand this expression. So I've got cos alpha minus cos beta squared, so I can kind of FOIL this out. And when I do that, I get cos squared alpha minus 2 cos alpha cos beta plus cos squared beta. That's this piece. Okay, and this is all going to be the square root still, but I got more to write. I'm going to do the same thing over here with the sine. And so plus sine squared sine squared beta minus 2 sine alpha sine beta plus sine squared beta. Okay. Now, if that wasn't clear, remember this part here is just that, and then this part here is just that. Right? So pause the video if you need to and verify that, but that's just expanding those things. Okay. And I've got a lot of squared terms in here, so I should be thinking of the Pythagorean identity because I'd really like to simplify this down. And so I'm going to regroup some of these things. I'm going to take the cos squared alpha and the sine squared alpha, which I wrote wrong. This should be alpha here. Sorry about that. That should be an alpha. Okay, I'm going to bring those two together, and then I'm going to do the same thing with the cosine and the sine of beta. Right, so this one and this one first. So I'll write sine squared alpha plus cos squared alpha. That's that and that. And then I'm going to do the same thing with these two. So plus sine squared beta plus cos squared beta, right? And that's that one and that one. And then I've got these two pieces left over that I have to hang on to still. So minus 2 cos alpha cos beta minus 2 sine alpha sine beta. And so I haven't really done much. I've just rearranged things a little bit. And it's all just addition and subtraction, so I can change the order of things. Okay. And so what the benefit of doing that is that this is equal to 1 and so is this, right? These are both 1, so I can get rid of a lot of terms and replace them with just a 1. Okay. And so I'm going to do that. I've got 1 plus 1 minus 2 cos alpha cos beta minus 2 sine alpha sine beta, square root of that. And then of course I can write that as, I should combine those, so 2 minus 2 cos alpha cos beta minus 2 sine alpha sine beta. Okay. And now what we're going to do is we're going to kind of pause, right? So hold that thought, right? We're going to pause here. Okay. Now remember, this was all taken just from diagram 1. Right? So we just looked at diagram 1 and we said, well, here's P, here's Q, so the distance formula tells us that the distance of this thing is equal to this expression. Okay. All right. So now what we want to do is we want to look at diagram 2. Okay. And we want to think through what PQ is in relation to diagram 2. Okay. So diagram 2, remember, it's the same triangle, so PQ, that distance should be the same, but it's got a different expression here, doesn't it? In this expression, P is just 1, 0 instead of cos beta sine beta, right? And in this expression, Q is cos alpha minus beta sine alpha minus beta instead of just cos alpha sine alpha, right? So there's a different, the distance PQ, while it might be the same distance, it's going to be expressible in many ways, and this is a different way to express it. So let's figure out what the distance formula tells us PQ is according to diagram 2. So for diagram 2, PQ is equal to, well, it's cos alpha minus beta minus 1 squared. Now where's that coming from? Let's make sure we can see that. I've got cos alpha minus beta and I've got 1, right? So it's just x. Remember the formula says x2 minus x1 squared, right? So this is like my x2, this is like my x1. Subtract them and square it. And the distance formula says I need to add to that the difference in the y values. And so similarly, the y values are sine of alpha minus beta minus 0 squared. So again, that just comes right off of the triangles. So you've got your y2 here and your y1 there. So sine of alpha minus beta minus 0. And you square it. We want to add those two together and take the square root. Okay, and then just like before, we're going to go ahead and we're going to expand this whole thing. And so this is the only piece that really expands. This is really just sine squared alpha minus beta. All right, so when I expand this, I get cos squared alpha minus beta minus 2 cos alpha minus beta, and then plus 1. So it's like minus 1 times minus 1, right? And that's this one. So this whole thing is that guy. But I still need to put this over here, so I can just think of the 0 as not being there, and I can write it as plus sine squared alpha minus beta. Okay, so that's the other piece. Okay, so I've got these two pieces, and I'm going to do something real similar to what I did previously. I'm going to rearrange, bring the cosine and the sines together here, and I've got like sine squared alpha minus beta plus cos squared alpha minus beta, right? And those two I'm going to group together. And then over here I've also got this minus 2 cos alpha minus beta bit. Okay, and so just like before, this is equal to 1, right? So I get 1 minus, let's see here, hold on one second. Oh, sorry, I forgot a 1 here. I've got this piece here too, so that should be plus 1. So I've got 1 plus 1 minus 2 cos alpha minus beta. Okay, and we know that that is equal to 2 minus 2 cos alpha minus beta. Okay. All right, so now I've got an expression for the distance PQ from diagram 2. Okay, so now we're going to bring these two together. Okay, so let's recap there just a second. So from diagram 1, right, you'll have to look back in your notes to see what that looked like, but from diagram 1, I found that PQ was equal to 2 minus 2 cos alpha cos beta minus 2 sine alpha sine beta, right? And that's the square root. And then from diagram 2, I found separately that PQ is equal to 2 minus 2 cosine, oh, sorry, that's a 2, I don't know what I was drawing there. 2 minus 2 cosine of alpha minus beta, square root. Okay, so these are two expressions for the same line segment, and so they're obviously equal, right? And so I can set these two equal to each other. So 2 minus 2 cos alpha minus beta is equal to 2 minus 2 cos alpha cos beta minus 2 sine alpha sine beta. Okay. Now I think if you're looking at this, you're probably thinking to yourself like, oh, I can see the kernel of the difference formula in here, right? I've got cos alpha minus beta over here, and I've got cos alpha cos beta sine alpha sine beta, but I've got these radicals and I've got these other constants and whatnot in here as well. All of those things will disappear in the end, right? So namely, I can square both sides and I get 2 minus 2 cos alpha minus beta equals 2 minus 2 cos alpha cos beta minus 2 sine alpha sine beta, right? So if I square both sides, the radical just disappears, right? And then I can, the 2's disappear as well. I've got 2 on both sides, so a positive 2 on both sides, and so I could just basically subtract 2 from both sides, and then I get negative 2 cos alpha minus beta equals negative 2 cos alpha cos beta minus 2 sine alpha sine beta, right? And then I could obviously divide both sides by negative 2, right? So if you think about that, right, everything cancels away, right? And then I get cos alpha minus beta equals cos alpha cos beta minus, or plus, because I'm dividing by negative 2, plus sine alpha sine beta, right? And so this is the difference formula for cosine, right? So that's where it comes from. That's where this guy comes from. Okay, and so this was just one of the difference formulas. A similar demonstration could be done for the remaining formulas. I'm obviously not going to do that here, but you can take the time and see that in fact a lot of the demonstration is really kind of similar, right? But here are all the sum and difference formulas. Here's all the sum and difference formulas. I'll write them out. So we've got the cosine of alpha plus beta. That's equal to cos alpha cos beta minus sine alpha sine beta. Then you've got the difference one that we just did. That's equal to cos alpha cos beta plus sine alpha sine beta, right? So obviously a nice symmetry there. When it's the sum of two angles, you know, you got the difference over here. When it's a difference of two angles, you got the sum, right? And then for sine, we have something similar. So sine of alpha plus beta is equal to sine alpha, cos beta, sine alpha cos beta plus cos alpha sine beta. Okay, so this the pattern kind of flips here a bit, so plus and plus, and then for sine you've got sine cos cos sine, right? So there's a pattern here, but it just changes for the different trig functions. And then finally, for the sine of alpha minus beta, you've got sine alpha cos beta, and then of course it's minus cos alpha sine beta, right? So here are the four sum and difference formulas. So this one we verified, right? We verified that one, but we could just as easily go and verify the sign of the difference. Now the sign of the sum is just a little bit of a different derivation, but it's along the same lines, right? So I would encourage you to go out and try to derive another one yourself, kind of using what we've done as a pattern. Okay. All right. Okay. So that's great. What's the value? What's the usefulness here? Let's do some examples and see how this can be useful. Okay, so let's do kind of an application here. So let's say we want to find the exact value of cosine of 15 degrees. Well, cosine of 15 degrees is definitely not on our unit circle, right? We've got 30 degrees here, but we don't have 15 degrees. So this is not one that we've seen before. Okay, so what is going to be the cosine of 15 degrees? Well, one of the things you can notice, so note 15 degrees is equal to 60 degrees minus 45 degrees, right? Now 15 is equal to a lot of things minus a lot of other things, right? But in this case, these are kind of nice because 60 and 45, these are angles that we've looked at. We know the exact values of the trig functions, specifically cosine. We know the exact values of cosine and sine for 60 degrees and 45 degrees. So we can use, so given this, we can use the difference formula for cosine. And here's how we do it. We say cosine of 15 degrees is equal to cosine of 60 degrees minus 45 degrees. Right, that's true, right? Right, and this is just like your cosine of alpha minus beta, right? And so we know, we can just reference the formula that we just wrote down. We know that the cosine of alpha minus beta is equal to the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. So in this case, it's equal to cosine of 60 degrees times cosine of 45 degrees plus sine of 60 degrees times the sine of 45 degrees. Right, so note here, alpha we're saying is 60 degrees and beta is 45 degrees. So kind of note that. That's where this is all coming from. Hopefully that's clear, but if it isn't, make sure you kind of think that through. And so then, well, we can say that we know what these values are. Like we could go look at the unit circle at 60 and 45 degrees, right? And we can see that here's 60 degrees, so cosine is a half, sine is square root of 3 over 2. And here's 45 degrees, they're both square root of 2 over 2. Right, so we can just plug all those values in. So cosine of 60 is a half, cosine of 45 is square root of 2 over 2, and then plus sine of 60 is square root of 3 over 2, and sine of 45 is square root of 2 over 2. And so we get this nice simple product here. And so we can add this together and we get square root of 2 over 4 plus square root of 6 over 4. And so you can leave this as an exact value, square root of 2 plus square root of 6 over 4. It's also probably fine to, well, no, we're looking for exact values. So we're going to leave it like this. This is the way you'd want to answer this. Leave it as an exact value and not a decimal approximation. Cool. Okay. Very good. So that's obviously a very useful, way to. It's a very useful formula because it allows us to find sort of exact values of odd angles that aren't explicitly on our unit circle, but are either the sum or difference of values on the unit circle. All right, there's lots of angles that would fit this characteristic. Right, so that's just one use case. Let's see how this can be useful when we're solving or verifying a trig identity. Let's say we want to verify, and I guess this is kind of a contrived example. Let's say we want to verify that the cosine of alpha minus beta divided by the cosine of alpha and cosine of beta is equal to 1 plus the tangent of alpha times the tangent of beta. Okay, so this is a little bit contrived because we do have this piece here that says cosine of alpha minus beta. But if you're given something like this, it's sort of a dead giveaway that, hey, you're going to want to use the sum and or difference formula. So we'll start on the left-hand side here, cosine of alpha minus beta over cos alpha cos beta. We can just expand that numerator, and we can specifically say that that's cos alpha cos beta plus sine alpha sine beta divided by cos alpha cos beta. Okay, and we can break this into two separate terms, right? You've kind of got this side of it, and then you've got this side of it. And so we could write this as cos alpha cos beta over cos alpha cos beta plus sine alpha sine beta over cos alpha cos beta. And the nice thing about that is that this is just 1. So this is 1 plus this. Right, now remember what we're trying to get to. We've got the 1 plus, but we need the tangent alpha tangent beta. But you can see that this is sine alpha over cos alpha, which is just tangent of alpha, and sine beta over cos beta, which is just tangent of beta. And so we have it. 1 plus tan alpha tan beta. Right, and so we've got the expression that we're looking for. Okay. Very good. Very good. And so we've talked about the sum and difference formula for cosine and sine. Let's see how, actually let's do one more example first, and then we'll get to tangent. Let's do one more example here. What about, let's see, let's try this one. Let's find the exact value of sine of 7 pi over 12. Okay, so 7 pi over 12 is not on the unit circle here. Right, we've got 7 pi over 4. We don't have a 7 pi over 12. 7 pi over 6. Definitely don't have a 7 pi over 12. Okay, so how can we figure this out? Well, we're going to use the same trick. We're going to note that 7 pi over 12 is equal to pi over 3 plus pi over 4. Now, what are those values? Well, this one here you can think of as basically 4 pi over 12, and this one here is 3 pi over 12, right? And so these are just reduced. But obviously 4 pi plus 3 pi is 7 pi, right? So this sum here is equal to that, and it reduces down to that. Now these are angles that we know. Those are angles from our unit circle. Right, so we've got pi over 3 and pi over 4 on here. So here's pi over 3 and here's pi over 4. So we've got those two. We got cos and sine for both of them. Okay, so we're going to use that to find the exact value. Okay, so remember we are looking for the sine of 7 pi over 12. And so we know that that's equal to the sine of pi over 3 plus pi over 4. Right? So we're looking for the sine here of the sum of two angles. Okay, and so you can kind of consult your formula, but you'll find that this is equal to the sine of pi over 3 times the cosine of pi over 4 plus the cosine of pi over 3 times the sine of pi over 4. Right, so this is like sine of alpha cos beta plus cos alpha sine beta, right, where alpha plus beta is up here. Right, so you can go back and double check that formula, make sure that you can see that. But that's what it is, and so we can easily see that sine of pi over 3 is square root of 3 over 2. Cosine of pi over 4 is the square root of 2 over 2. Cosine of pi over 3 is a half. And sine of pi over 4 is again square root of 2 over 2. Right, so this whole thing reduces down to square root of 6 over 4 plus square root of 2 over 4. And so kind of similar to the last example, we'd want to leave it in that form there. All right. Very good. Very good. And let's move to the tangent function. So the tangent function is also going to have a sum and difference formula. So what about tangent? Well, the tangent formulas they go as follows. They're slightly different. So you got tangent of alpha plus beta. So that's the sum of two angles. What's the tangent of the sum of two angles? Well, it's equal to tan alpha plus tan beta divided by 1 minus tan alpha tan beta. Okay. And the difference formula looks very similar. Tan alpha minus beta, that's going to be tan alpha minus tan beta divided by 1 plus tan alpha tan beta, right? So the signs just all flip. Same exact structure, but just flip the signs. All right. And so this one could be used in pretty much the same way as the sine and cosine, right? So if I want to find the tangent of an odd angle, I can use this in the same way to do that. It can also be used to verify identities. So let's do that. Let's do an example there, verifying an identity. So let's verify that the tangent of x minus pi over 4 is equal to the tangent of x minus 1 divided by the tangent of x plus 1. So that's got a nice look to it. Okay, so let's verify this. So we'll just start with this side. Tangent of x minus pi over 4. Right, and we're just going to basically plug in the difference formula for tangent. And we get tangent of x minus tangent of pi over 4 divided by 1 plus tangent of x times tangent of pi over 4. Okay. Now, the thing to notice here is that tangent of pi over 4, that's a number, right? That's an angle. There's not a variable in there, so we can actually figure out what that is. And the tangent of pi over 4 is like sine of pi over 4 over cosine of pi over 4, so it's 1. And the same thing down here, this is equal to 1 as well. So I'm just going to write it like this, right? But you get tangent of x minus 1 divided by 1 plus tangent of x times 1. And this is pretty much it, isn't it? Right? We just got to flip the orientation here a little bit. So the top is done, right? This is what we're aiming for. That's what we have. So we have tan x minus 1. And then the bottom is 1 plus tan x. We could just as well write that as tan x plus 1. Right? And so we went from there to there. Basically one step. Maybe 2 steps. You could think of it as 2 steps. All right. Very good. So that is the sum and difference. That we just went through the sum and difference formulas. So there's a sum and difference formula for cosine, a sum and difference formula for sine, and then also a sum and difference formula for tangent. And we went through a couple of examples of how to use it to find odd angles, exact values of odd angles, and also they will come up in identity verification as well. Right, though a lot of the examples where we've used it so far are a little bit contrived, but we'll see later where it can come up and be a little bit more subtly used. Okay, all right, so we'll leave it there, and next time when we get together, we will discuss additional trigonometric formulas. We'll get into the double angle, power reducing, and half angle formulas. Okay, so until then, take care.